Today I'm going to be talking about JNI obfuscation in the Android operating system. First, a little bit about myself. Like I said, my name is Ramgattie. I am a junior security analyst at Independent Security Evaluators. Currently, I am pursuing a bachelor's degree at East Stroudsburg University, where I'm getting a dual major, so I'm getting a degree in computer science and a degree in computer security. And my hobbies include cryptography and reverse engineering. So like I said, I work for ISC. ISC is an independent security firm. We're located in Baltimore, Maryland, and we're dedicated to aggressive defensive strategies using advanced science. I want to give the agenda so we all have an idea of what I'm going to be talking about today. So I'm going to be giving some background knowledge on Android. Then I'm going to be talking about what JNI is, what code obfuscation is. I'm going to be giving a code example so we can actually see what JNI looks like. I was talking to one of my friends before I actually started giving this talk, and he was telling me that he had a very hard time compiling native code. I was lucky, my code actually compiled, so at least we'll get to experience that today. I'll be doing some static code analysis from the APK that was generated from the JNI example code, some dynamic code analysis from the APK that was generated from the JNI example code. I'll be talking about some of the problems that we face with obfuscation, and then I'll be talking about some of the solutions. So first, Android. Android is a mobile operating system. It is currently the most popular mobile operating system. It is built on the Linux kernel, and all applications are Java-based. I want to talk a little bit about the Android build process, so you understand what I'll be going through today in order to reverse the application. All Java bytecode is, well, first you have a Java application, then it's converted to Java bytecode, and then Java bytecode is translated into DEX format, which is the dollar executable format. Applications are distributed in APKs, and APKs are just zip format packages. So I have this little graph that shows the build process, and it's just 3 simple steps. Your Java source code is converted to Java bytecode, and then after it's translated into the dollar executable format. This is the Android software stack. I'm going to be going a little bit more in depth in this one. So the Android software stack is divided into 4 parts. It has the application layer, the application framework layer, the native user space, and the Linux kernel. So in the applications layer, we have things like system applications and user applications. System applications is, for example, like settings, that's a system application. And user application could be like Chrome or whatever other browser you're using, that's an example of a user application. In the application framework layer, we have Android framework libraries like the Power Manager and the Package Manager. We have system services like the Power Manager service and the Package Manager service, and core libraries like Apache Harmony. And then after we have the Android runtime, the Java runtime and Zygo. I didn't include the Dalvik virtual machine because the Dalvik virtual machine is currently being phased out as of Android 5.0. And then in the native user space, we have native daemons, the hardware abstraction layer, and native libraries. These small parts here, but you don't use them that often. These were the 3 most occurring parts of the native user space, so these were the ones that I included. And then we have the Linux kernel, which includes like drivers, like audio and video drivers, and Android shared memory. This was also I took this graph out of a book called Android Security Non-Internals. It's an open source book that this guy, Yuri, wrote for his master thesis. So let's say, for example, we have so all the applications that are in blue, or all the little squares that are in blue, are written in Java, and all the ones that are in green are written in C or C++, because it's the native language for Android. So let's say we have something written in blue, like for example Chrome, that needs to speak to something that's in green, like a native library. The native library, I guess you can think about it, like, for example, OpenSSL. OpenSSL is a native library, and every now and then Chrome does need to use TLS. So let's say that this Chrome implementation was using OpenSSL as from the native library. So we need to have a way for applications in blue to talk to applications in green. So I drew a red arrow that shows Chrome talking to a native library, and a dotted line symbolizing the JNI. The JNI is the Java native interface, and that's how Java applications speak to native applications, which in this case is Java talking to C or C++. So in case that wasn't too clear, I drew this little graph it just says that, like, let's say we have an application that's running on the Android runtime, and it needs to speak to a native library or something from the hardware abstraction layer. So, as you can see, the red arrows go both from the application to the native library or the hardware abstraction layer and upside down. It's because JNI is not only meant for applications in Java to speak to applications with native code, it's also meant for applications that have native code to speak to applications that are written in Java. So a good question is, why not just use Java? Why not just have all your libraries written in Java? So just not have native libraries. Well, there's a good reason for that. I mean, we do have this whole thing with Java being that you can just compile it once and run it anywhere, but it has its limitations. So for example, we have the ARM version 8 AES. So ARM version 8 AES is a hardware acceleration for Android. So newer devices have this instruction set available, and it makes AES implementation a lot quicker. So I'm guessing a lot of you do a lot of source code analysis, or you do a lot of encryption with your applications for the developers. Sometimes when you have to encrypt, it's going to take a long time, and you don't want your users running an application that takes a long time because then they get cut up a bit, and we just use another application. So I don't know if any of you have newer devices or work on newer devices, then I would probably use ARM version 8 and JNI. Then we have platform-specific code, like I/O control or input or output control. This Java doesn't have implementation for this. This is only written in native code, so you would have to use native code. And then you have libraries in C or C++. So for example, SQLite 3, a lot of people like SQLite 3. If you're going to use it on Android, you're going to have to use JNI. So why even obfuscate code? Why not just have the application be as it is? The first reason is to hinder reverse engineering. I work in a security firm, and every time I see code that's not obfuscated, I think it's the best thing ever because it really saves me on time. On the user or the developer side, I feel really sorry for them because it was a really easy fix, but they didn't do it. Then also to identify code that's optimizable. Soon I'll be talking about a tool that optimizes code. What it does is that first it optimizes it, reduces the code, it optimizes it, and then it obfuscates it. So not only does it help hinder reverse engineering, it helps optimize the code. And it also helps remove unused classes, fields, and methods, which could be considered part of optimizing code. So the tool that I'm going to be talking about specifically today is ProGuard. ProGuard shrinks, optimizes, and obfuscates code. So when it shrinks, it removes unused classes, fields, and methods. So whenever sometimes you'll be writing code, or like your developer will be writing code, and they'll make a lot of methods that aren't really necessary. In my example today, I'll be showing you how I wrote code that wasn't very necessary, and ProGuard just optimized it. It also uses control flow analysis, data flow analysis, and partial evaluation to remove code that's not used. So not only does it shrink it, but it also says like, hey, there's a shorter path this way, you should probably not do this huge rigmarole, but just go directly to it. And it obfuscates so that it takes class names and it makes them short and meaningless. So that, for example, if you have a class that says return password, it'll take that class and just rename it as A or B or something else. And when you're generating your APK, you have to have your project configuration file, and in your project configuration file, you can have a ProGuard configuration file, or a ProGuard configuration section, where you can set that you want it to be optimized, or in this case, just obfuscated. So for now, I have some JNI example code that I'd like to share with you guys, which is right here, and I need some to zoom in a lot. Great. So, is that better? Really? All right. 1 second, guys. All right, I'm going to assume that you guys can see it now. I really can't see it, so this is a problem, but whatever. All right, so the first thing that I want you guys to look at is that there's information between static brackets. So the reason why that is between static brackets is that when you load your Java code, it's the first thing that loads. Because if you run into a situation where you're using a library that's not loaded first, you're going to get a linking error, which is not what you want when you have code. And then a little bit later on, somewhere down here, you'll be able to see that there's a library, or there's a call to string from JNI, CDB. What that is that it's called to a C++ implementation of that method. So it's the native code that was loaded from this library. So, and then later on, then after what it does is that there's just text field. So what the application does is that it loads, and then after when you click on a button, it just calls a native method and it returns a string. It's pretty simple. And then this is the implementation of it. Shorter version. There we go. This is the implementation of that method. And what it does is that it just returns a string. That's all the JNI method does. Back 2 slides. Alright, so now I would like to do some static analysis of that APK. So let's just suppose that it was all, we used ProGuard, the APK was already generated, and everything's okay. It's already on the device. So like I said before, APKs are just zip format packages. So the first thing that you have to do is just unzip the package, or the APK. And then after you unzip it, the next thing that you would have to do is just use dex to jar. So whenever you have an Android application, when it generates a dex file, like I said before, so Java bytecode is translated into dex format, and then there's this tool called dex to jar that what it allows you to do is that it can convert dex files back into jar files. So as you can see in red, dex to jar is the application that is called, and classes.dex is the dex file from that APK. And now it's time to actually look at the code. So first thing to look at is just that all the methods are, or all the classes are have meaningless names now, except one. So all of them are like A, B, C, but there's that one method that didn't get its name changed. Well, that's kind of weird because we told ProGuard to obfuscate all of our code. Why didn't that happen? So let's just go to that method. I guess it's that. It's not that. So, as you can see in the method, it gives you, this was without source, we didn't have source code. I straight up this down, have the APK, unzipped it, and used dex to jar. But that looks a lot like source code. The reason why is that whenever you have Java bytecode, you can immediately transfer it back into its original form so that it looks pretty much the same. The only thing that's different is that we don't have meaningful names anymore, we just have these letters. And then all the other things are just, well, except that one method that's test JNI activity. So now that we know what that is, that'll probably be very handy if we decide to do dynamic analysis. Because for now we can just see that there's that method, but we don't really know what it does. There we go. Alright, so now that we have the target has been acquired, we know what class it is, and we know which one we want to stop on, we can just start doing dynamic analysis. So, first thing I want you guys to know is that your device should be rooted because we will need root access on the device in order to do dynamic analysis. And second thing I want you guys to know is that if you are going to do dynamic analysis on an application, the application has to be debuggable. In order for you to make the application debuggable, you have to edit the Android manifest file. So just as file as Android manifest.xml, just put in that field that's in red, and the application is not debuggable. And then one of the things that we have to do first is to make sure that the device is available. So just plug in your device with the application installed and make sure that it's available. So just run jwp which is the Java debug wire protocol, and it'll list the bugs. And then after, we have to get the PID for the application, or list the PIDs of applications that are debuggable, which in this case is that one, the one in red. And then after, we need to figure out if that's our application. So if you just run PS and grep for the application's name, you'll get the PID, which was the same. And then the next thing that we have is that we need to forward the connection for it, so that if you just use ADB, this is for us to be able to debug on our computers itself instead of on the Android device. So after we do that, you're able to use ADB to debug the application. So after forwarding the connection, you should be able to attach to the process with JDB. And what JDB is the Java debugger, so that you can just pause on whichever process you want. And first thing that I did with JDB is I listed all the available methods. On the bottom of the screen, there is a very familiar method that's in red, and that's the test JNI activity method that we want to stop on. So once we stop it there, there's a problem. Why was it that we weren't able to debug a Java application, or why weren't we able to debug this application with JDB? Does anybody know?
Because you can't separate points on data methods.
Yes, thank you. So now we get to use GDB. So for probably a lot of people don't know what this is. This is the GDB fish. It's called Archer. It's because it's an Amazonian fish and they shoot down bugs. So food for thought. There you go, Archer the fish. First thing that we have to do is that we have to get all of the information out of the APK, so we unzip it first. After we unzip it, we have to make a directory that contains all of the system root application, all the libraries and binaries from the APK. I'll talk about why we need those in a second. So first thing we do is we pull out all of the libraries from the device. So just use ADB pull and pull /system/lib. And then we do the same for /system/bin. And then, like we already prepped for JNI, we know what PID is. And we have to push GDB server onto the device. So GDB server also needs to be compiled as an ARM, as the ARM version. I would suggest compiling it yourself. If you can just download the Android NDK and push GDB server onto the device, and it works fine. So then after, make sure before you run GDB server, make sure that you're root. So that's why you have to have a rooted device. So it's sudo to become root, and then GDB server, and attach to the process that's in red. And as you can see on the bottom, it's listing currently on that port 1, 2, 3, 4, 5. And then again, we have to forward that connection because it's going to be a different port than we did with JDB. So that's 1, 2, 3, 4, 5 for both. And then we also need to have GDB compiled for ARM, because the normal x86 one will not work for this device. So that we need to use ARM version of GDB. This is also part of the Android NDK. So if you are going to be doing native code, and if you are going to be debugging native libraries, you will need this Android NDK. So the reason why we downloaded the library before from the device is that we will need them when we're debugging the application. If not, JDB is not going to find all the symbols, and we're not going to be able to debug the application. So if you're really good, you can probably stop on the exact memory locations. If you are really good at that, let me know, because I'd like to learn from you. It's very hard. And after in GDB, we need to set the remote target, which was our local host and the port that we forwarded before. And after doing that, we can start debugging the application. So the nice thing about GDB is that you can just tab along and find the respective application, which in this case is Java_com_example_test_JNI, whatever, and you can stop on that application. Then once you broke on that class, you can just step through it and eventually fall on the right call and get the contents. So I know this one doesn't seem as interesting because we already knew what the string was because it was part of the Java bytecode. However, what I was trying to show was that you can just break on whichever function you want and get the information out of it. So like, for example, if we were using Chrome with OpenSSL, we could just break on the OpenSSL call and see what key was being used. So the question is, why did obfuscation fail? Why didn't we tell ProGuard to obfuscate all of their information? So the reason why is that you cannot rename identifiers on either side, so you can't name something on Java or C or C++ without changing it on the other side to match. So to make that a lot more clear, here's some actual source code. So on the Java code, you can see example1.run, which is the method for the example1 class being called. And then in the C implementation of it, you can see that it's called Java_example1_run. So the reason the naming convention is what allows Java to call C, or for it to find the corresponding method. So what I'm trying to say by this is that the JVM mangles the name so that I can find it. So the reason why it was named Java_example1_run, it was because it was the only way for it to figure out where it had to go to find the corresponding method. So like I said, example1.run, the corresponding definition for the method in C or C++ would be this name, so that it knows that's a Java method with an example1 class, and their method's name is run. So the TLDR for my talk is that if you have to write apps using JNI, and you don't want them to be reverse engineered, you're going to have a really long time with you, because JNI calls aren't obfuscated when you use tools like ProGuard. You can get it to obfuscate, like you can specifically tell ProGuard obfuscate these methods, but then you're going to get linking errors, because it's not going to find the corresponding method in C or C++. How do we solve this problem? When you do JNI, we can get rid of the obvious names, so that whenever somebody's trying to reverse engineer our application, they don't just look for the one with the longest name, which is what I did when I was doing my presentation. So the first solution is using this thing called register natives. So the problem that we're facing is that functions need to be named in a certain way in order for the JVM to find out what the native implementation is. So, like I said, example1.run, it'll be Java_example1_run. The solution is that you can use register natives so that whenever your C++ implementations have to call it, it can find a pointer towards it, make it a lot easier. So instead of the JVM having to locate the implementations of the native functions by the exact name, you can pass function pointers along to find them. Alright, time to look at some more source code.
There's no automated tool that just obfuscating matches.
There is no obfuscated tools for that to work.
It wouldn't be that hard
for some reason, because the implementation of how it works, ProGuard only works on the Java implementation. So you would have to make a way for ProGuard to also work on C files. Sorry, I guess in all honesty, probably like maybe 2 or 3 weekends of coding later, it would probably work. But the people at ProGuard have to figure it out. Some more source code. So as you can see by this much longer implementation, this is register natives. So we went from being like 3 or 4 lines to a much longer implementation. The reason why is that there is this matchup table that shows somewhere here. Okay. That shows what the native method is going to be mapped to. So it passes a function pointer along from string JNI from CDP. It's now mapped to another method with this name. So, and the corresponding method, or corresponding definition for that method, just returns the string. So the register native call is just going to map the Java function names to function pointers in C or C++, or Fortran, or whatever it is written in, and then it will just find that method definition within the JNI file and return that method instead. So this is great and all, because you don't have to deal with source code that doesn't work, because you will not get static errors or linking errors. So are there problems with the solution of registering natives? Sadly, yes, there are problems. The first one is that it replaces an object structure or export a symbol table with another object structure, the Java class names and signatures. So obviously you can just find a file, figure out where they're pointing at. And it can also be neutralized by tracing the register native calls with the debugger. So you can just find out when that call is, whenever that call is happening, and find the corresponding call like C or C++. And it only helps hide calls from Java to C, but it doesn't help hide calls from C to Java. But we have a second solution. The problem is that the method names are often meaningful, so we just look for the long method name. And the solution is just manually rename all those classes to short names. So like when we were looking with static analysis, the method names are just like A, B, and C. So why not just name the method as the same thing? So instead of being test from JNI or return from string, you could just make it Z or X or whatever you want it to be. So more source code, great. So this is the second implementation or the third implementation of the source code that I wrote. It's still loading the same library. However, the method name changed. It's now much smaller. And if you look for the corresponding one in C or C++, the method name is also small. So that whenever you're going to look for this obfuscated code, you're not going to find it. Despite how painful this is, it's pretty fun. Because I like prepared everything, I was like, I'm just going to keep a separate tmux thing, have everything in it. Then you think about presentation mode. If I could ever figure it out. Alright, we're going to need after. One more. Great, back to it. So the problem with solution 2 is that developers must deal directly with the obfuscated method names. So that's really bad for the developer's part, because usually I just use AG and grep whenever I'm writing something. And if I'm going to grep for the letter Z, I'm pretty much going to get back to the source code that I was actually looking through. Also, like it's going to make life a lot more difficult because these method names are no longer significant. As if on the developer side, you have no idea what's going on anymore. So whenever you change something, it's going to have to be done once in Java, also once in C. And there's no built way of turning it off. So, like I said, every time a developer is going to write new code, it's going to be a living hell. He's probably not going to want to work for you anymore, or do it anymore. Also, it only helps hide calls from Java to C and not calls from C to Java. So my suggestions are that if you do not use JNI, do not use JNI unless you completely need to use it. So unless it's one of the reasons that we specified before, if you're just writing JNI code for kicks, don't do it. It's not worth it. And if necessary, make sure that your code is obfuscated. I would honestly prefer to do with register natives, especially for next time around when you have to write code. It's going to make your life a lot easier. This code should be updated pretty often. So, any questions?
So you were working on Android. These techniques and the security implications, obfuscation, and so on also apply if you were running Java on Windows or some other desktop.
The methods would probably work exactly the same. The only thing that would change is that you wouldn't be using GD. You're probably using like something like Windebug or Ollie, for example, instead of just using GD. Any other questions? It actually makes it a lot faster most of the time. It's very rare that you can use register natives and it makes it, and the performance actually declines.
Is there any advantage, so when you're demoing you're debugging like on a real device, right? So is there any advantage of using a real device over using that?
So I tried using the emulator. The emulator makes your life very difficult, especially when you're trying to pull stuff off of it. So the reason why I use my own device is that whenever I was trying to debug something, the emulator would just crash on. So the emulator crash is really awesome compared to normal OS.
Especially you would have to, normally with the emulator, you use x86, right? Right, you gotta use the version that matches the library size, and then use more, which is slow.
Else?
Still a little stuff on why there's not an easier way out of this side of it. You can see the same problem for years.
Yeah, so you are right. So the question was why hasn't anybody figured this out yet? Honestly, you wouldn't know because it doesn't seem like that. It's been a problem for years. So it's honestly something that can be solved pretty easily. The problem mostly lays in function pointers. So ProGuard doesn't find the corresponding function pointers, which is why the obfuscation never really works. So you can try writing native code and just mapping and running your ProGuard and obfuscating the method in Java, but you are going to get a static rank. That's the problem for now.
Say you have your PC side, your program, load some dynamic library runtime that design the Java was called how is it let's keep that version deal inside of it.
Has it ever come across any manually obfuscated machines?
We have. We have professional stuff with manually obfuscated JNI code, which is great on their part. I think honestly that's one of the better solutions. But like I said, for developers, it's just a little help because they wouldn't know where to look for the corresponding methods.
But yeah, as I was thinking, if nobody's even manually doing it, they didn't find any value in hacking.
Yes. So my original I have actual source code that uses data encryption with OpenSSL, so it does it significantly quicker. So instead of using JavaX.crypto, if you use OpenSSL significantly quicker, so I would use the JNI code. And you can't see that you can't stop on that method and extract the key. It's just like I did with GDP.
Renaming the method is only one part of it, right? As long as the method boundary is still there, that doesn't address any reverse engineering concerns or making it linear the number of functions to figure out which one's which. Right?
Yeah. If there aren't any more questions, that was our presentation. Nice having you guys. Thanks for attending my talk.